Hey, what's up, math people? We are going to be talking about exponential growth and decay equations today. These things are super useful too. Just like last video where I said this is the most important thing, not the most important thing, but it's important. Yeah, I don't know, it's important. You're gonna have to learn exponentials if you want to go into science or anything like that. So we're gonna learn them. They're pretty cool. I have fun. So let's get into it. So the first thing you want to know about is the model. And when we say model, we're not talking like trains, right? Like, what do trains look like? All right, hang on. Let's start back over. Train. It's got like a smokestack, right? It's got some choo-choo. Box. Yeah, I don't know. It's a train, right? Okay, we're not talking like train models here. We're talking like this thing will give us an approximate answer, but it's just a model, right? It's not the real life thing. We don't actually measure every single fruit fly and go count every single atom of an element, or you know what I mean? Like, it's impossible to have a really, really exact answer because of chaos theory and all that good stuff. Most systems are chaotic in real life, at least. So when we say model, what we mean is this thing is an equation that sort of does the same thing real life does pretty good. It's not perfect. It's not going to tell you that of the 9,326 fruit flies, 4 of them are missing one leg on the left side because of inbreeding. And it doesn't tell you anything about the carrying capacity based on the number of dog poop sitting in your backyard. And, it doesn't account for that stuff. But it'll get us a pretty good idea. So yeah, we're gonna learn how to get a good idea of stuff today. So let me walk you through this model for exponential growth and decay. It's the same thing. The difference between growth and decay is this k is gonna be positive for growth, and k is gonna be negative for decay. And you're gonna go, what is k, Bart? And you're skipping around too much. So let's maybe label this equation really quick so that we can understand what this thing even is. So we have p of t. So this is a function name. This is not p multiplied by t. This is population as a function of time, meaning I tell it time and it tells me population. So this is population for this equation. That doesn't mean we always want population, and it works on things besides populations of fruit flies. So you want to just think about this p of t as your final amount. That's final amount of whatever the thing doing the exponential thing does, This p subscript 0, this is a subscript, which means it's like a note to ourselves. It doesn't mean multiply by 0. It doesn't mean divide by 0. God forbid. Ugh. Right? This is just the fancy way that people say this is the initial value. You might see like p sub 0, that's initial population. You could see like t sub 0, that's initial time. You could see v sub 0, that's initial velocity. Having a little subscript of 0 just means it's the starting amount for whatever that variable is. All right. E is Euler's number. And it looks funny. It's pronounced Euler. So this number is a constant. It never changes. It's kind of like pi, where it's an irrational number that we know about that never changes, but you don't want to write out 3.141592655, whatever, right? You don't want to write them all out, so we just make a little symbol for it. So this is like that. It's an irrational number. It's called Euler's number, and it's about 2.71. I forget if it's 2 or 4. I think it's 714. But it's a number, right? There's a button on your calculator. It's like e to the x. Just use that thing to plug in the e with an exponent. Cool. All right. K is our growth rate. And this thing is always going to be really ugly. It's going to be some stupid decimal. It's going to be like negative 0.65, blah, 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 right? It's going to be ugly every single time. And this growth rate is kind of responsible for making sure the units work out and everything has the appropriate scale to it. And this K, we could probably do like a whole lesson just on how K works and what K does. But for you guys, it's a constant. It kind of tells you how quick stuff grows. Cool. And then T is time. There you go. Cool. There you go. That's the equation we're going to use. So we are going to use this thing. Some people call it the exponential growth equation, or it's an exponential. Okay. We're going to use this thing to solve just 2 problems today. I looked at your homework. There's like 4 of the first type of problem and then like 6 of the next type of problem. But just because it's fruit flies or bacteria, like changing out the thing that's growing doesn't change the way the problem works. So really you need a growth example and a decay example. So we're going to go do those. All right. Here are your steps. You're going to notice there's only 2 of them. These 2 steps are like grown-up college kid steps though, where when I say do step 1, you might have to do 3 or 4 different things to get step 1 done, right? But I believe in you guys can handle it. Okay. So our first step is we're going to use the given information to solve for K. The very first thing you need to do is find K. And of course, I'll show you how to do that. But you can't get the final answer without knowing K, and you can't guess K, unfortunately. There's not a nice pattern that I could tell you where you get to skip all the steps. You have to just go do some solving exponential equations. You put your big boy pants on, and you gotta go get your hands dirty in some math. So we're gonna do that. Then once you have K, you're gonna use the initial amount, K, and whatever the time you actually want to know the amount of stuff at, and then you just shove this stuff back into the equation and then type it into a calculator and it spits out the answer for you. So the real work here is going to be in step 1. Step 2 is plug it in and hit enter. Okay, cool. So let's look at example number 1. It says cesium-137 has a half-life of 30 years. For the people who care, cesium is a radioactive element, and when we say cesium-137, this is a particular isotope. Even if something is cesium, the element is determined by the number of protons, but some elements can have different numbers of neutrons stuck in the nucleus with it, and that vastly changes the properties of that material. So when we say cesium-137, this is the atomic mass, meaning there's 137 things in the nucleus. So that's what that means, in case you care. A half-life is if you have radioactive stuff. So let's say you've got like your lump of radioactive material here, and it's just like beaming off radioactivity. What that actually means, what radioactive stuff is these cesiums are so unstable that the little atoms inside the nucleus are kind of bouncing and jiggling around and hitting each other and all that. And eventually they jiggle so hard that it just flies apart and it'll shoot off some stuff. And then this will turn into something else. It won't be cesium anymore. It'll be, I looked it up. I think cesium decays into barium, but basically, this radioactivity, the stuff that gives you cancer, are tiny pieces of this atom that fly off and damage your cells and stuff, and that's what makes you sick. But radioactive stuff is just, there's so much stuff going on in there that it jiggles itself apart and flings off radioactivity. Yeah. So a half-life is if you let radioactive stuff sit on a shelf, after a certain amount of time, here, watch this. Copy. I should be an animator, you guys. Paste. Okay. After a certain amount of time, what happens is half of it disappears. Boom. Half is gone. That's what the half-life is. So after 30 years, half of your cesium is gone. And then after another 30 years, you would think, oh, the whole thing will be gone. But that's actually not the case. What happens is the rate at which it is turning into something else is exponential. So it kind of slows down. And then instead of having none left, you have half of the half left. So it gets cut in half again. And then you'd have an eighth, and then a 16th, and so on. So the half-life just tells us how long before half the stuff evaporates and turns into radioactive stuff. Cool? So that's the background info for that problem. It doesn't matter for the problem, but I just think it's interesting. So we've got some cesium-137 that has a half-life of 30 years. If you buy a sample of 100 grams for yourself, grams, Spartan, what else are we measuring grams? You guys are immature. As a graduation present, how much will be left when you retire in 47 years? All right, so let's get into it, right? So we are going to solve our exponential growth model. Let me just write it down for you. Okay, we want to work on filling this in, and our first step is finding that K model, or not model, but our growth rate. So we know the initial amount. It tells us you start with 100 grams, and it tells us how long it takes for something to happen, 30 years. Okay, if you have a half-life, what that means is in 30 years, only half is left. So we know how much there is at the end of those 30 years because I know how much I started with. So the ending amount after those 30 years will be 50 grams because half of it evaporates away. Our initial amount is 100 grams. E is a number. K is the variable we're looking for. And T is the 30. All right. Now we have to solve for this K. So you're solving an exponential equation. So our base with the exponent is just this piece. So we need to isolate that first. So we're going to divide both sides by 100. The hundreds cancel. 50 over 100 is 1/2. I'm going to just put 0.5 because we're going to be doing most things in decimals today anyway. And that equals e to the k times 30. Now to solve this, you have to think back to the last lesson, and we have to rewrite this as a logarithm. So we're going to have log, and our base is e. So I'm going to write natural log. This is the same thing as log base e, but because the base is e, that's special. It happens really often, so they gave it its own thing. So it's a natural log. So the argument is whatever the exponential equals, so this, so put the 0.5 inside the natural log, and logs equal exponents, so 30k. Now we have to get k by itself, so we're going to divide by 30, but we have to figure out what this number is first. I already went and got that. The natural log of 0.5 is negative 0.6931471.8 ... It keeps going, but that's where my calculator quits, so I'll just leave it like that. Equals 30k, and then you divide both sides by 30. And we have K equals negative 0.02310449. Ta-da, there you go. You are halfway done with the steps, but you're like 80% done with the problem. This was the hard part, was finding that growth rate. Now, it's actually not a growth rate. You can tell because it's negative. That means it's a decay rate. Right, and we know that, right? We started with 100 and it's going away. We're losing some. So this is an example of exponential decay. So now what we need to do is take this K and the rest of the information from the word problem to figure out what our new final amount is. So we're just going to go back through this equation, plugging in the information we know. So we are looking for the final amount. So we're just going to leave that as P of T equals, we still know the initial amount. Just because we know the rate doesn't mean magically that rock that you bought 47 years ago got bigger. You can't go back in time and change the size of the rock. So we still start with 100 grams and we put E to the K. I'm going to put K here, but we know it, right? It's this number. And now we want to know what happens after 47 years. So instead of putting 30 for T, we're going to put 47. Okay. So now all you have to do is type in 100 E to the power of 47 times this number K. So it's going to look like P of T equals 100 E to the negative 0.02310449 times 47. Type this whole thing into your calculator, and then whatever number it spits out, that's your answer. The number it does spit out, just so the people at home know, is 33.76, and I'm rounding a little bit there. And that's grams of cesium-137. Cool, there you go. That's how much of your rock you're gonna have left after your 47-year career. Cool. All right, let's go do a growth one. All right, so most life on Earth grows at an exponential rate. And because I hate lying to you, I'm going to tell you a short story. It says while below the carrying capacity. This is a lie. You don't actually grow at an exponential rate. You grow, like, I guess technically it's exponential, but it's not just e to the power of kt. You follow what's called a logistic curve. Right, and this is not on the test, right? You can zone out for it, like text your friends, see what they're doing. But what it is when you, that's actually a terrible graph for this. Let's do this. Okay. There's a thing called a carrying capacity. So like right here, this is like how much life something can support. Like could you put 1 million people on a 15-foot boat? No. Like either the boat would sink and you'd all die, or there would be mutiny and you'd like throw a few people off and then they'd still die. And it's just a hard limit on how much life something can support. Think of this as like how much food's available. If there's not enough food, not everybody can eat all the food they want. So either everyone's going to starve together, or like some people are going to get just barely, they're going to get what they need, and then everyone else starves to death, right? So it grows and it looks exponential, but at some point as you start approaching this carrying capacity, you're going to level back off and meet it. So it's not a true exponential, but I digress. For high school, it's an exponential rate. Okay, so here's the actual problem. If there are 5 fruit flies initially and 43 after 2 days, how many will there be after 7 days? So this is a little bit different. They're not telling us the half-life or something like that. But what's important here is they have told us a starting and an ending amount, and they've given us how much time it takes to get there. That's all you need. They do that here with the half-life. They tell us the starting amount, and then the ending amount is implied by the word half-life here. Here it's not implied. They just overtly come out and say there's 43 of them suckers flying around in 2 days. Now we want to know how many will there be in 7 days. So we are going to use our exponential growth model to figure out that question. All right. The first thing we need to do is plug in our final, starting, and time so that we can go and get K. And then once we have K, we'll fill in this side of the equation and find out our final amount. So there are 5 fruit flies initially. That's P naught, or P sub 0. P naught. Not is like an English way of saying none. And when I say English, I mean like European English. It means 0. It's just the way some people say it. So we have 5 things to start with. E, we don't know K. We're going to find that. Remember, E is a number. That's a number, not a variable. And it took us 2 days. And at the end, we had 43 fruit flies. So now we need to go solve this thing. So of course we're going to divide by 5 to isolate our exponential. So we get 8.6 equals e to the 2k. And you can change the order. Multiplication is commutative. The order doesn't matter. So now we're going to rewrite this as a logarithm so that we can get our variable out of the exponent. So this is going to be natural log, because our base is an e, of 8.6 equals 2k. Then you put natural log of 8.6 into your calculator. That is 2.15176 dose equals dose k. Now we just divide both sides by 2. So k equals 1.07588811. There we go. So now we have k. This is our growth rate. Now we just take our growth rate. We're going to plug that thing back in right there. And we're going to put in our initial amount and the time we want to know, and that'll tell us our final amount. So our final amount is going to be 5 e to the k. And then where t is, we're going to put 7 because we want to know after 7 days. So this is going to look like P of t equals 5e to the 1.07588811 times 7. Type this whole mess into your calculator and then it'll spit out the answer. So in 7 days, we are going to have 9,326, and I'll tell you the decimal is 0.4 or something, but you can't have 0.4 of a fly. So I would just round like that. Just drop it because it's a living thing and you can't really have decimals of living things. So we're going to have about 9,326 fruit flies in 7 days. Now, just because it's interesting, right? And so lesson's over. You're done. Go home. You get out of here. If you don't give a hoot about math, pause the video. Get the heck out of here. I don't want to tell you interesting stuff that you don't care about, right? I don't want to, oh yeah, math is it's pretty lame. You can go now. Go ahead and sign off. All right, cool. Now that all those nerds are gone, people who care about math. So with these fruit flies, you can't. Have you ever walked into your backyard and been like, there are 9,000 flies? Maybe, but that means you need to pick up your dog poop a little bit more. But realistically, there's not going to be 9,000 flies. Do you have any idea what 9,000 flies looks like? It's like if you took like a soda bottle and filled it with flies. That's probably like a couple thousand, like 2 or 3. It's probably like 5 or 6 soda bottles, like 2 liters, filled with flies. There's not that many flying around your backyard. Unless you live on like a farm and you have horses where there's literally hundreds of pounds of horse poop laying around, you're not going to have this many. So that kind of goes back to that carrying capacity. If you live in like an apartment and you just have like one or two flies buzzing around, they can't grow at some crazy exponential rate because of this carrying capacity. Back to the carrying capacity. This is telling us if the flies have an unlimited carrying capacity. So we just took our whole house and we smeared poop all over it. Your mother would be livid, right? I mean, you take poop and you wipe it on the tables, and you take poop and you wipe it on the walls, and you take poop and you wipe it on the toilet seat. So when you go to poop, you're sitting in poop. Then we'd have this many flies. In real life, you can't get this many flies. Even in a backyard where you've got like 20 dog poops laying around, there's not enough poop to feed all those flies. You feel me, dog? So again, this is a model. We're just guessing how many flies there would be. We're not taking into account how much poop you've smeared around your house, you know? Okay, all right. I really just wanted to say poop a whole bunch. That's what it was. I wasn't going to tell you any cool math, but... All right, so you probably have homework. You probably don't have any questions because I taught that so well. So go ahead, get the heck out of this video. Go start doing your homework. Are you seriously still here? Dude, go do your homework. The video's over. Get out of here. I'm serious. All right, fine, I'm leaving.